Ladies, gentlemen, cyborgs, welcome to the one and only, at least I really hope it's one and only, otherwise I'll feel kind of bad about my... Ah,
Me? Did I do it?
how does this keep happening? Everything's terrible. Anyways, ladies, gentlemen, cyborgs, welcome to the one and only Voidstar Lab. Today, well, we're starting with, today we're doing something a little bit different, because for the second time in Voidstar Lab history, but for the first time on purpose, I am joined by a special guest. And we're not starting at the bottom. We are going to the tippy top. Whether you have a Prusa, whether you've got whether you've played around with like the Rheology printers, whether you built your own Voron, 9 times out of 10, if you are involved with 3D printing, you have used an E3D product or a knockoff E3D product at some point. Yeah, they're the ones that make like the heater blocks, cartridges, nozzles, all kinds of cool stuff. And today I'm joined by their co-founder, Sanjay Mortimer, to talk about his favorite subject. Well, to distract him a little from work and talk about his favorite subject, not so much the extruders, but the stuff that goes through the extruders. Welcome, using our brand new interview view. Welcome, Sanjay, to Voidstar Lab. How's life?
Yeah, pretty functional. Yeah, I guess the background for this is I saw Zack was like, oh, I want to do this like all the filaments thing. And at work, the joke is always that like I'm a plastic enthusiast. And I guess if I wasn't doing extrusion systems, I'd be doing like filaments and materials and stuff like that. So yeah, it's my like big thing that we've done a little bit of in the past, but if you want to really do something well, you've got to do one thing and really concentrate on it. So I don't get to do nearly as much like
So
material science shop
what
work.
actually got you that? So like, was it the material science that got you into making printers, or is it the printers that got you into material science?
I definitely say printers into materials. Um, I think that there's not quite a quote, but something that was said by a guy called Alexander Slocum, who's a prof at MIT. And he has this like running theory that the Industrial Revolution was born entirely from the tapered needle roller bearing, which allowed us to make precision machines. And the tapered needle roller
Right.
bearing came from our ability to control the carbon content of steel. And if you look back through like all of human technology, every great leap forward starts with a material science leap forward. And I think that PLA was the big like material science leap forward that trivialized the ability to make low
PLA is pretty good
cost.
stuff.
Yeah,
But
like
you don't think
there's a
it's
huge
you don't
break.
think it's the end of the line.
No, and this is where it gets like really, really cool is when you get into this like burgeoning field that's very fashionable now, like design of materials, like what Elon's doing with the custom 300 stainless or the aluminium lithium on the Falcon series, and or well, it's the same 300 stainless in the Cybertruck, but this like making application specific materials is something that now the DuPonts and the Dows and the Eastmans are piling in and making FDM specific thermoplastic polymers, whereas before we've always had to like steal them from
Yeah, I
the
noticed.
injection molding and extrusion
I
industries.
noticed that as I was buying these materials, like there are a whole bunch of these were either they were either like either mentioned on the product page they were intended specifically for 3D printing, or they were formulated for both conventional manufacturing and 3D printing. Like there's this flexible plastic I was playing with called Arnitel. There's
Yep.
PVDF. That was a tremendous amount of fun to print. It wasn't. Uh, oh man, yeah. But like, what was
Did
really
you
cool
enjoy
is
your
they're
hydrogen
mentioning that they're
fluoride for
designed for 3D
breakfast?
printing. So I guess like the question that's going to be on everyone's lips here is, so if PLA is old school, right? What should they use instead? What are the plastics of the future? What are all the kids going to be 3D printing with in 20? I don't know how old am I? 2025? Is that the future? I guess it's not. It's only 4 years
Yeah.
away. 2100. What are kids going to be printing with in 2100?
Um, I think we're still going to have like PLA is still going to be a big thing for a good while, but highly engineered polyesters of the PLA is technically a polyester. I don't get into that, but like yeah, the PET, PCTG, polycarbonate kind of blends with lots of
Ooh.
different cool that people are just starting to figure out how to engineer the filler systems
Hmm.
for that. And also, I think that um, like fill and PBT as well in a big way. And filled nylons that are low cost and easy to print, but still have amazing properties. I think that those are going to be the materials of choice for scaled manufacturing with FDM as an additive
Ooh, that's a
manufacturing
pretty
process.
loaded phrase in of itself. Scaling FDM. Like you
Yeah,
think that because yeah, there aren't a lot of there are very few companies that maintain like print farms and actually do any sort of scaled manufacturing using 3D printing. Like Prusa is
I would
probably the
like to
best known.
protest that statement, I guess. It is this is like something that we're seeing more and more of. And when I go and talk to Ultimaker, they're starting to sell like cells of printers, like racks of them. And it's like this like mid-scale manufacturing. And I think it's important to not see this as Toyota are going to adopt FDM,
Right.
but the next wave of inventions and small businesses and people that cater to these niches, FDM will be the manufacturing process of choice rather than defaulting to injection molding.
That's pretty bold, but I guess you're the ones with the intel on this. I've been hearing a lot about I think what was it? I think Elon Musk SpaceX kind of kicked it off, but there was recently a video on Veritasium and one on
Yeah,
I
relativity.
think in Tegs's channel of like printing rocket engines and stuff. I guess like the thing that I'm thinking I guess is is 3D printing starting to eat like CNC machining's lunch? Like, is it starting to
Well,
become
funnily
more
enough, like
practical to print than machine?
if you go and talk to these guys, like the Mark Forged and the Desktop Metals, and like their biggest customers are machine shops, and a lot of these places are printing jigs and fixtures, and like then on the metal side, they're printing like near net shaped parts for
Hmm.
post machining, so that they instead of starting with a piece of square stock, they start with a near net blank without having to get into forging and casting tooling. Um,
Oh, that's interesting. Why replace CNC machining with 3D printing if you can machine the printed part?
yeah, yeah. And
I know some maniac made a multi extruder printer and designed and designed a tiny CNC mill that replaces one of the extruders.
yeah, yeah. That's a bit bonkers, and I want to see that fly. Um, I really don't know where that ends up. I just know that it was a lot of fun. I can't decide whether it's a good idea long term or not. As in whether that like whole
It is tough to
way of
evaluate,
doing things.
especially because like a good CNC mill just has more axes. It just needs a CNC like a CNC mill is much needs just much more freedom of movement than a 3D printer. Like because a 3D printer can build stuff sort of from the inside out by making it in layers. A CNC machine has to be able to turn and get under it.
Yeah, and then you also like look at the complexity of. I mean, we use tons of Swiss lathes, and I just like I you know, you're never going to hit like 5 micron cylindricity, like lights out, like 30-second cycle time machining with FDM. That is such kind of different beasts. But
Huh.
I think that where like FDM steps in is that ability to, if you have like a water jet or plasma cutter, an FDM machine, and a CNC lathe, there's not much in the world of mechanics that you can't make, like big, strong structures, high complexity electronic housings and latchings and mechanisms. And if you look at even just the great designs of 3D printers, you end up seeing aluminium extrusion mixed with like printed parts for the complexity and geometric freedom. And
Right.
just seeing all of those, like FDM is the most cost-effective way to engineer a huge amount of complexity into a part with the lowest setup cost, like hands down.
So we've got a couple. So like a couple of things to take care of first. First, I realized that I never shouted out the folks who are actually paying the bills for this episode. These guys are paying the bills for a future episode, but this particular stream is sponsored by Things. So no matter what material you print out of, if STLs are involved, head to things.com. Use the link in the description. You can get my projects there, and you can easily upload and share your own stuff. Thanks a lot to Things for sponsoring. We'll talk a little more about them later. But the big question, the thing I brought you here today, is to talk about materials. So we talked before about like PLA is sort of like it's sort of this. Not so much the state of the art, but it's what everyone uses now. And it seems like in the future, people will be moving on a bit to, like you think people will be moving on to kind of purpose-built materials designed for higher throughput. Yes. But what about right now? What do you think are so like, I imagine a lot of people in the audience have only printed in PLA, maybe a little PETG, some ABS, maybe they got fancy, did some carbon fiber. What are they missing out on? What are some materials that every maker should try?
I think that everyone should have up their sleeve some reinforced nylon of some description. Yeah,
well, that's a good one.
Most likely that's going to be a carbon reinforced nylon. Because that is by far the best performance material that you can easily squeeze out and make parts on pretty much any 3D printer with an abrasion resistant nozzle. It's just this like huge leap in performance.
Is there a particular brand you like?
I really like the materials that are, and the Luvicon materials, which are the ColorFab PA, PACF, and they're engineered, and the material science is done by Lehman and Voss, and they also then sell that to a couple of other brands. I think Mitsubishi Chemicals do some, or I'm gonna have to watch my words before I go into it. But
people are asking in chat about if there's a fire outside, and yes, I'd like to inform everyone that Sanjay's house is on fire. We're trying to complete the interview before he's consumed by the flames. No, there's a barbecue going.
Yeah, I'm on pseudo holiday, so. And this is what I
might have gone a little too heavy on the lighter fluid there.
Yeah, but We have a North American friend who's dealing with the barbecue based stuff. Um,
I
and
I don't know about you, but like from building a lot of electronics, my nose is just hypersensitized to the smell of anything burning.
yeah,
Like I imagine it's for you it's like that but with plastics.
yes, um, yeah, that's funny. Like all the plastics that all have those particular smells. And the one that gets me the most is whenever Tolman is okay. I have to watch my words. You can smell the different manufacturing locations of nylons
Huh.
because when you print wet nylon and it comes wet from the factory, what you're actually smelling is the water bath that it was run through. And so different nylon manufacturers have, let's say, different levels of hygiene about the water baths that the nylon runs through.
Well, you're telling me
Um,
when I ran that nylon trimmer line through my printer, what I was smelling was actually sewage water?
yes, that is exactly it. And so you can certain factories have a little like a specific stank to them,
Huh.
which if you've been around for a while and you know the different places that these things get extruded in, you can you can smell that like
Oh man, that's
I'd
hysterical.
say that Tallman is a bit swampy. So my friends are
For
giving me
for folks who aren't familiar with it, for folks who've never printed nylon, nylon is notoriously obsessed with sucking up water. Like if you
yes.
basically a spool of nylon left out for any amount of time is going to be like 2% water by weight or by mass. And no matter how high quality it is, it always has to be dried out and dehydrated before you use it. It's like the amount of water it absorbs and how aggressively it does it is like preposterous. So
It's
yeah, I
the
guess there
OG
could be enough
foaming
in there that you
filament,
can
right?
smell it
It's
as it
got its
boils.
own built-in gas generator. Who cares about AZDP or whatever it is that goes in the color
So
fab
so I get one
foaming?
thing that I'm really curious about that kind of relates to this is like so I have my let me see if the camera is working correctly. Oh, I pointed too far down. Well, here at Voidstar Lab, we've got the 3D printer closet loaded with all the different filaments and stuff. Yeah, there we go. Yeah, so we've got our 3D printer closet loaded up with all our different filaments. And I'm wondering if E3D has something similar because you must be testing all kinds of plastics with all kinds of products and making sure everything's intercompatible. So is there just like a giant like Indiana Jones style archives full of filaments?
Yes, including like all the unreleased ones that never made it. So we have like we have a really great relationship with pretty much most materials manufacturers because we don't compete with them, but all material manufacturers, it behooves them to ensure that like their material is going to print well through an E3D hot end. And here at E3D, we want to be able to print any and all materials. So like we're always backing and forthing and testing out new stuff and giving feedback. So yeah, from like Color Fab, Lehman and Voss, DSM, Eastman, DuPont, all the big boys, like, but also all the little guys as well. Like, the, you know, there's like handcrafted experimental Toolmans. God, I remember getting the first flexible materials in and like thinking we were so funny with the things that we printed. Um, and
Is it safe to say what you printed in front of the children listening?
no, clearly not. Um, yeah,
So like,
yeah.
so where's the is there like a scheme that you guys use? Like, is there like a checklist? Like, someone comes up with this brilliant new nozzle design, and you shove them this piece of paper with like 50 filaments listed on it, or is it more that you just you know print stuff on it and see what happens?
I generally just like throw it at Greg. I'm like, yo, Greg, what you think of this? And try and give him as like as little warning or like preconception as possible. Because Greg has sampled like every filament from here to Kingdom Come from like the highest performance, like molecularly re-engineered peaks all the way down to like recycled fishing line that has been harvested out of the oceans, to like, you know, take waste stuff out of the waste stream and reprocess it into
So he
useful
just
goods.
runs all these different things through it, and then he's like,
Yeah,
"Buddy, you forgot to drill the hole in this nozzle."
yeah, and I guess that's the thing. Every time you think that you've come up with some like comprehensive checklist of things to print or ways in which to like prove or make a material fail, something new will come along and like totally blindside you. Like the like recently, like a lot of recycled materials, they behave, they change viscosity like midway through like segments of spool, because they'll go from having some like high molecular weight material to something that's been sitting around in the sun for 6 months. And so they'll be like, if they're not very well homogenized, you'll like end up changing
Huh.
viscosity partway through, and all your retraction and everything just like all goes to hell in a handbasket. That was with some like recycled nylons.
So you met so like
Yeah,
when we talked earlier, you met I asked you what your favorite filament was, and you actually gave me a couple answers, because the one you said was number one. You said it wasn't really on the market. You said it was this custom peak blend that you tried a while ago that blew everything else out of the water. Like, is that is that like super secret, or is there anything anything you can tell
yeah.
the
Without
crowd
naming
about?
names, I still, yeah, it's a bit of bone and contention that hasn't hit the market yet, and it's kind of being held up.
So then
We
what would you
ended.
say is your favorite that is on the market? Because you mentioned before carbon fiber nylon, but like would you consider that your absolute favorite?
I'm a really big fan of the recent Prusa PC blend and the PCCF.
It's good stuff.
That's really kind of pushed the envelope in terms of performance per, like, the important thing isn't like outright performance, it's performance per unit hassle. And like it's true though, right? Because we don't print like carbon reinforced peak, and there's a reason for that. It's because like
Oh
it's
my
in,
god.
like, you think nylon's hygroscopic, like you let peak out of
The carbon
you know.
fiber peak was the worst material that I've printed for this video so far. It was as brittle as spaghetti. It clogged the nozzle if I looked at it wrong. It as it was cool as the print was finishing. As the print was finishing, I just happened to look at the manufacturer's website, and I read on it, warning: if you let this completely cool off while it's still in the nozzle, it will permanently destroy it. Like,
Yeah,
everything about this filament was as bad as possible.
yeah, and yeah, that one still puzzles me because I still don't know the exact failure mode by which that happens. And it happens on a lot of the semi-crystalline polyketones. And people are always like, "Oh, yeah, it's because it crystallizes in the nozzle." But I don't buy that for a second. But anyway, that's a whole other distraction. No, I think that because when you and I say like performance per unit hassle, in a manufacturing context, that means performance per unit yield, um, and performance per unit capital expenditure on equipment to print it effectively, performance per unit human intervention in looking after and tending and caring for these, which all resolve themselves to ultimately the like high level fitness function of performance per unit cost. And so as we make materials that from our perception are pushing the envelope in terms of, oh, I can now get a really high performance carbon or glass reinforced polycarbonate,
Probably
in a
slight overkill.
manufacturing context where we have like scaled manufacturing, that is meaning that we are improving the performance per unit cost. Um,
Huh. It's interesting stuff. Huh.
And
But
that,
like
that is what I
for
find
people
most
printing at
exciting.
home, the math is. I'd imagine the math is even more aggressive because I feel like for a lot of I would guess that for the majority of people with 3D printers, they don't have time to like learn how to like print a high temperature material. Like they don't have the time to remember to take the nylon out of the closet and start dehydrating it before they go to work.
Yeah,
Like they're
and,
not
and
like
all of that, it just
they don't
sucks
even
so
know if you'll
much.
be able to
And
print that
so
night.
this is why I really, right at the start, I was like, the high performance polyesters with fillers in them. So talking about those polycarbonate PET, PCTG, PBT, um, like the Eastman Tritan type stuff, the Prusa PC PET blend type stuff. That those materials are really you're getting very close to the printability of PLA, but you're starting to push up right into that like fairly extreme engineering polymer performance bracket when you're getting into the PBTs and PCTGs and PCs. And then you start putting in fillers. And at the moment, everyone's using carbon. And I guess my big prediction is that in the near future, we will stop using. The reason why everyone uses carbon, and this is the big like dirty secret of the industry, isn't because it's the highest performance material. It's because carbon is smaller in diameter, it's a smaller fiber, and compared to glass, which is much cheaper and has almost all of the same performance properties, or in terms of performance per unit cost, is much, much better, which is why you see tons of glass reinforced nylon and not a ton of carbon reinforced nylon in tools and under the hood of your bonnet. It's because carbon goes through nozzles easier. It goes through small holes, and it's because it's smaller in diameter. You can get it broken into smaller, little shorter chunks, and it's available in that like milled short state, and you can just get it and pour it in.
So do you think this has to do with like the fact that the 0.4 millimeter nozzle is standard instead of something a bit wider gauge? Because in my opinion, in my opinion, like I don't I don't know why most people use a 0.4 millimeter nozzle. I don't know why it's the standard. I think it should be 0.6 at least. But yeah, do you think it
I can tell
do
you,
you think that
tell you a funny
affects it?
story. So when when um when we were starting out, zero point 0.5 was the most common size that you could get. J-heads came in 0.5, Lulzbot were using 0.5 on their British nozzles. But the cheapest drill bits that I could get that was small were 1/64 inch drill bits, which I believe is 0.396,
Yeah, it's in the
which
neighborhood.
if you round it out is like 0.4. And so I could get all these tiny little drill bits and they were really cheap. And so I was like, well, these will make a hole that's small enough. And yeah, so that's why we have
Huh.
0.4, I think.
So
Yeah,
it's your fault. Everyone's using a 0.4 millimeter nozzle. You did this.
I think I think 0.4, the popularization of 0.4 is probably on us. But it was always in that range, right? I'm not gonna
Yeah.
like take like it was always like 0.35 to 0.5 was the common kind of range before we were on the scene by a long way. But I think that, well, the reason we settled on 0.4, and I think that that had quite a bit of knock-on effect, was, yeah, drill bit availability.
Huh.
Anyway, but yes, and that is why fillers. So my big prediction is things like mica, like fillers, glass balls, custom re-engineered, like glass whiskers and stuff.
I've got a
Basically,
filament here filled with nanoscopic diamonds. It's got diamond dust in it.
Yeah.
that type of
I
stuff. Yeah, that would be cool. As I'm printing with all these different materials, like yeah, carbon fiber kind of sucks. The filaments filled with Kevlar or the ones filled with Kevlar, filled with raw, even stone particles, fiberglass. They just are so much more predictable than carbon fiber.
Yeah, and so I think that one thing that I'd like to, so the reason having fillers gives you two things. One is that you get an improvement in certain mechanical properties. You sacrifice a bit of toughness and you gain stiffness and temperature deflection, higher temperature deflection. Um, but and that's just from a material performance standpoint. But from a processing standpoint, the addition of fibers is a huge help in making materials that normally want to warp like crazy stay put.
Well, I got some
Because
carbon fiber ABS, and the print was just it was perfect.
and so if you get one of the first, I think the first carbon reinforced material was Protopasta PLA-CF. And I really like that material, and I recommend that people go check it out, right? Because PLA is already like hella dimensionally stable. And then you add in the carbon and you get out this material it is just immensely stiff. Um, it's not super strong in terms of like ultimate tensile strength, and it doesn't, it's PLA, so it's brittle, and then you add carbon, it's super brittle. But my God, is it stiff? And because the PLA isn't shrinking very much to begin with, and then you add the carbon in on top, when you print these parts, like they are just so dimensionally perfect. Like even really huge parts. So whenever we want to print a really precise jig or fixture or something that needs to really stay put and have like dimensional stability when it's a really large part and be really stiff, PLACF from Protopasta is one of those things that we reach for. Um,
Yeah, it's really good plastic. It's particularly brittle.
yes.
Yeah, one of the most common misconceptions that I've seen is people think that people think of carbon fiber as strong, which is a problem in of itself. But they
Yep.
think that carbon fiber filament is stronger than the regular stuff. And in reality, you'll tell them it's the total opposite. It's far more brittle. Like carbon fiber is added for stiffness, not for strength. Here's the question.
This gets really complex, right? But it is possible for us to make materials stronger with carbon fibers. I think I've lost you on the audio, by the way, Zach.
The which?
I don't know if that's better. There we are. Yeah, cool. We're good. We're good.
So
I
yeah,
guess my point is that it is possible for us to add strength and even toughness. I know it sounds crazy, but impact toughness by adding fibers. It's just that we haven't gotten good enough at engineering these filler materials yet, and the filler packages, so that we get like nicely dispersed, high aspect ratio fibrous fillers. Because the dirty secret of the carbon filled filament industry is that these bits of carbon are, I mean, I have some pictures of some stuff under the microscope, but the aspect ratio on some of this, it's like 3-1, 5-1. It's like these tiny little chunks, and then it gets broken up even more by coming out the nozzle. And so really what you have is like carbon dust a lot of the time. And so the carbon's in there and it's hanging out, being expensive, adding some stiffness, but mainly just being small and something that doesn't shrink as it cools. And by doing so, it means that you can take a really warpy plastic like nylon or polycarbonate and make it stay put and make it print well.
huh? Does that also affect other materials, or is that a carbon specific thing?
And it's not a carbon specific thing. But milled carbon is one of the few things, like it being carbon fiber sells filament, which is like a big, it's like, oh, it's carbon fiber. And so people buy it. You're like, people will pony up $50 for a spool of like 500 grams or something because it's got carbon fiber written on it. Don't tell me like you haven't done it, Zach. Like you sit there and like laugh at all the filthy casuals, but we all got sucked in once upon a time.
You might underestimate how much of a cheapskate I am.
Right. But if you think that you're a cheapskate, like you have no idea how much of a cheapskate the manufacturing industry is.
Yeah, I could imagine.
All of these properties are achievable without the use of expensive carbon fillers. And so by using highly engineered forms of dirt, so like wollastonite and mica and steatite, which are, if you look under the hood of your car, you'll see a lot of like parts that are labeled PPMF, which is polypropylene mineral filler. And an entire industry outside of 3D printing, conventional manufacturing, has been built on how much dirt can I add to the plastic? Because people have figured out coupling agents that mean you can use high performance forms of dirt and actually improve the performance. But in the past, it was just that the dirt is cheaper than the plastic. So the more dirt that we can put in the plastic, the less the part costs, right?
But it's not just a cost reduction strategy, because mica's temperature resistance is bananas.
Yes, but before people figured out what's called coupling agents, the mica was just there's a difference between filler reinforced polymers and filled polymers. And this is a really important distinction. So in the past, polypropylene, you could only add dirt to it, but the dirt and the polyprop wouldn't stick together properly. And so they weren't coupled. And then there was this huge revolution when chemists figured out a way to prime the dirt and add what's called a coupling agent that would let the polyprop and the dirt bond together. And as soon as that happened, there was this like explosion, because now polyprop, the cheapest of the cheap in terms of processing and just base cost, now suddenly you had this like temperature resistant, stiff material that you could make high performance automotive parts that could withstand chemicals under the hood at like 120 degrees centigrade. And this was an explosion. And whereas before you'd have to use expensive materials like glass coupled, like nylons and things like that.
So can you buy 3D printer? Can you buy mineral filled 3D printer filament? Because I haven't seen it.
No, and this is what I'm saying, is this is what I think is coming, is that same revolution that happened when people figured out how to engineer really low cost filler systems for to take mediocre plastics and make them high performance and dimensionally stable and temperature resistant. I think that we're on the verge, and I would advocate for and encourage everyone to be looking at like adding mica, glass balls, like mineral whiskers. There's tons of great fillers out there that are high aspect ratio, like these mica flakes and mineral whiskers.
The aspect ratio being like the physical size of the particle relative to the size of the nozzle.
Yes, and so you want something that's at least one order of magnitude smaller than the hole it's coming out of. Is the like general rule of thumb. Oh, nearly dropped my laptop. Yeah, it's the general rule of thumb. So it's 10x. And you want something that, if you want it to flow and process easily and really stably, you want something that has a reasonably like high aspect ratio. Or what's really nice about mica is it's flakes, and flakes have lots of surface area, but they're not hugely directional like fibers are. And so This means that you get parts that are less likely to shrink differently in the XYZ planes. So the most dimensionally stable filler that you can add, the most dimensionally stabilizing filler that you can add is glass balls or glass bubbles, because they're truly isotropic or isodimensional. You can't get more isometric, like isometric.
I
You know,
I remember from our resin
uniformly.
printing that when you add like a glitter, I mean, for the only glitter that really works in resin is mica based because the flakes are thin enough. But
Yep.
when it's printed, the flakes end up going parallel. They end up being driven. They end up being driven parallel to each other. Does the same thing happen when you 3D print
Yes.
it?
So with all fillers that have an aspect ratio, because of the properties, like what we call the rheological properties of polymer melts, i.e. just like how stuff is as it flows, the molecules of the polymer all get squished. And imagine you take some silly putty or blue tack and you cut up some like copper wire, into little flecks, and you mix it all up in your hands. And just try this as an experiment at home. Get some blue tack, which is, like polymer, and get some stranded like copper wire and mix it all up. And you've got it all like, random and all over the place. That is what the resin is like when it's in the pellet format. And then when we put it through the extrusion system first to take it from pellet format to filament, you're stretching it. So if you take that blue tack full of randomly oriented copper fibers and you stretch it 10x in one direction, all of those fibers are naturally going to end up being pulled slowly into such that their axis is aligned with the axis of extension. And then we do that again inside of the nozzle. And again, on the outside of the nozzle, when we flatten it and go in the other, and we keep going. And so we're doing this and we're doing this. And you could do that with like large flakes of glitter, like you would with mica. And when you do this inside of a resin 3D printer, you are trapping between, it depends on your system, but you've got the two planes of the resin printer, the print and the like FEP film in a lot of cases,
Right.
and you're like doing this. And what's happening is the material is flowing. When the two planes come together, the material has to spread outwards. And so it's essentially being stretched, kind of like you've got a ball of pizza dough and you're stretching it out in all directions flat on a surface to form it into that like flat pizza. But imagine you put a load of like pizza toppings on the pizza ball and then stretched it, odd way to make a pizza. But if you did that, all your pizza toppings would end up flattened and aligned in the direction that you stretch your pizza. So
That's really interesting. So is there a
phenomenon.
way to get around? Is there a way to mitigate this? Is there a way to get around it, or is it just an intrinsic part of the fabrication process?
It's intrinsic, but what you can do is use a filler that doesn't have direction. So if you use a filler that doesn't have directionality, so if you put balls into your blue tack, so you get some BBs and drop them into your thing, that they don't have an orientation, so they don't really care which way you stretch them. And this is neat because when you align all these fillers inside of your material, what you create is a system that, as it shrinks, it's able to, as it cools, sorry, use my words correctly. As it cools, the resin in between the particles is going to shrink. And because these fillers are axial and have alignment, as the material shrinks, you get different amounts of shrinkage in the parallel to flow and perpendicular to flow regimes. And so if you go and look at the data sheets for a lot of glass and carbon reinforced material, you'll see a mold flow shrink rate, or there's a lot of ways of measuring this, but they will give a parallel to flow and perpendicular to flow shrink rate
So what?
number, and
So what
they
you're
will often be
saying
different
is that folks who
by
print a lot
fiber.
of carbon fiber and stuff should probably run a calibration cube, because the way that your carbon fiber filament and your fiberglass filament and all that cool stuff, the way that comes out is going to be different than a pure polymer.
Yes, but the problem is that then if you change the direction of your infill, your calibration cube is going to change
Oh, that's
dimensional,
interesting.
right? Which is interesting and
I
inconvenient, like a
feel like
pain
we
in the
could probably show that
backside,
off for an episode.
right? But that comes down to this like performance per unit hassle.
Hmm.
Like, oh my God, now I have to think about like every single direction of piece of G code that I'm putting down that like, oh, boring. So instead, what if we could have fillers that were a bit less fussy and dependent on how we put them down? Because the carbon, like, is not doing anything for you, like in terms of like this is the big lie. So you're getting like all of the pain in the ass of having a highly directional fibrous
Right.
filler. You're paying for carbon. You're getting like all of the negative side effects, but you're sure as hell you're not getting carbon fiber performance, boys and girls. Like, I'm sorry to break it to you, but it's the truth, because this is like most of the carbon that you're using kind of sucks or from the frame of reference of what people would consider acceptable from a thermoplastic composite, what we are using is kind of laughable.
So I'm just going to cut you off for a split second here, because it seems like we've got a super chat. Alex, thanks a lot for the rubles. I really appreciate it. Thanks for supporting the channel, and glad folks are interested in this. This is kind of a new format. Like, I don't know. I feel like every twice a week talking to myself for a bunch of hours is getting kind of old. So I'm glad folks are liking the mixing it up a little bit. Yeah, we've got we had an interesting question here from Valdarg, who asks about synthetic spider silk, and what about stuff like that, like organic additives, or is it just rocks and minerals that matter?
This I find really interesting, right? Because one of the big challenges with carbon and glass is the fiber has to come out of the nozzle, and it's usually going to be oriented in the direction of flow, and then all of a sudden it has to turn 90 degrees, and the fiber does not enjoy this at all. So you end up, if you ever like printed a bad carbon or glass reinforced material and it looks and feels fluffy and sharp, that's fiber stick out. It's the fiber piercing like out of the surface of the polymer, and it stops like your layers sticking together. It's just a sucky thing all around, and this is why we have to use quite short fibers. But what if we could have like aramids or spider silks or other like directional longer length fibers that could bend? What if we could print Vectran or Dyneema or even just ultra high molecular weight polyethylene suspended in? This I find really, really interesting. And this gets like, these would be very complex systems. And yeah, I don't
Hey,
know.
we're all nerds here. We want to hear about it.
Yeah.
Where is all the ultra-high molecular weight polyethylene filament anyways? Because that's a really
UHMW
common material outside 3D printing.
Yeah, UHMWP is not a material that flows very nicely. And that's just by virtue of its molecular weight, right?
There's really, really long molecules.
Yeah, and so when you go and you buy Delrin from DuPont, you can get it in a range of viscosities or molecular weights or whatever you want to call it. They're all the same thing. And so if you have a complex part with thin walls that you want to run and shoot really quickly, then you might choose a low molecular weight material. And that's like having, the best way to think of a polymer melt is like spaghetti in a bowl with like some sauce thrown all in it. Like imagine you make a sauce out of like lard, right? Something kind of sticky. And so you've got a bowl full of cooked spaghetti and lard. If you want to then get that,
it sounds like a standard lunch here in America.
Yeah, if you like, you want to take that and rearrange it. If you've got really long spaghetti, that's going to be a pain in the backside. You're going to need to like pad and prod and squeeze all these different chains like into line to get them to flow. So it's going to be a much like more stodgy, thick melt. Whereas if you cut up all that spaghetti into like lengths that were 1/10 the length, the effective viscosity of this like new polymer melt with lower molecular weight is going to be much easier to shape. And that's why like your canned SpaghettiOs are all low molecular weight spaghettis, right? Because otherwise they don't go into the can nicely. That's the cold hard truth.
I find this really interesting because one of the materials I tried out for this next for the Every Filament episode is aramid filled nylon, basically Kevlar filled nylon. And
which one did you print, and was it any good?
Yeah, I found it actually very easy to print. Yeah, usually these filled nylons tend to be kind of tricky to dial in. They tend to.
I've been trying to find a good aramid filled nylon for a long time.
This one was all right.
See this in action.
It was a little on the expensive side. But hey, if you bear with me one sec, I'm just going to pull up the. Oh man, I was supposed to be. I made myself a checklist and I just didn't use it. I just have this giant bin of every 3D printed boat here. Bear with me one sec. Let's see. It is Filamentum brand nylon AF80 aramid.
Yeah. All my friends think I'm weird because I'm set up here.
Yeah, I believe. Hang on a second. Hello. I got my big bin of boats here. I'm going to switch over to the.
We're talking about aramid filled polymers.
Are they waiting? Are they waiting for you to come to dinner? Because if so, I admire your priorities.
I've told them don't expect me to come to dinner. I'm talking about plastic. Thanks, bro. I might come down for a beer.
Let me see if I can actually hunt this thing down.
But I love plastic more.
I'm gonna. Oh man, yeah, I know that Brooke puts up with a tremendous amount. She puts up with a lot of baloney to allow me to do these episodes. Let me see if I can hunt this thing down here, because it was one of the first plastics I printed.
Yeah, that's the only one that I know of.
There it is.
And
here we go.
I've had a crack at printing, and it's pretty decent. But it's also not like outstandingly exceptional or like mind-boggling. It's good, and it behaves kind of like I expected it to. But what I'd like to see is essentially and this is where I think this is like things that I would love to do if I wasn't doing extrusion systems, and so I'm going to talk about it probably a bit more freely than I should, but I want someone else to do it anyway. Is I think the future is hybrid reinforcement systems, and I think that the use of combinations of fibers, including aramid fibers and glass and mica fillers, and so you could have like aramid fiber that is adding that like high aspect ratio strength ability and adding the toughness, but doing so without causing all of the pain in the backside of carbon that doesn't want to turn the corner or glass that doesn't want to turn the corner. And then so now you've got a whole pile of toughness, and you can throw in some glass and mineral, to add in the stiffness and temperature resistance, and you're not going to end up with something brittle because it's all jacked full of aramid.
Yeah, this is what
This is
you
what I
see
think
on
the future
screen
looks
here is the nylon aramid benchy, and you can see that it had a little trouble with heat absorption on the top, but otherwise the detail, like for nylon, this is really good. Not for nylon, you can't use a cooling fan or anything because it'll cause it to warp. So getting dimensions like this is actually pretty impressive, and this was the first one I ever printed. Like, so I didn't even dial this in. I didn't actually have enough of it to print 2 of them, so I had to be very careful. But yeah, the quality is actually really impressive, and it's very light.
And the surface finish compared to most carbons, if you give it a give it a bit of a stroke to polish it like a genie, it'll feel smooth and not rough. And that's because you don't have any of that like fiber stick out nastiness that you would with normal fill polymers, right?
Huh. I'll make myself a note to give it a bit of a polish for the episode.
I don't mean polish as in make it shine, but like imagine you're shining a genie's lamp, you know?
Yeah. That's pretty interesting.
Yeah,
That's another thing. Now I'm thinking about it. Like we just kind of like take for granted that, oh man, I realized I put your face and my face backwards in the inset versus the scene. I'm a real professional here. What was I saying? I think we just take for granted that like if the filament has stuff in it, it's gonna be matte. And sometimes you don't want that. Like sometimes you're gonna want a stiffer print, but you're gonna want it to be a little shiny, a little glossy, or just straight up smooth, maybe low friction.
Yes, and oh no, I can't steal someone's thunder, but it's an academic paper that's coming. I think it's shit.
I think it's safe to assume that very few people in this audience are going to read it.
So let's just check that it has shipped.
We're in the bleeding edge here. Tebla from the chat says Hobgoblin Gold man has good taste.
Yeah, I do like a good Hobgoblin Gold.
I've never even heard of that one.
Yeah, Hobgoblin's like that.
Well, while you look it up, yeah, right. So just for the audience to know, we're doing yes, we are doing a follow up to our every filament episode. This one's gonna have a tremendous number of filaments, like literally this. Oh no, that's the wrong button. There we go. Yeah, this is like the boats I've printed so far, and this isn't even all of them. This is just. Yeah, we still have a bunch of flexible materials I haven't been able to print yet. We've got like all the support filaments. I haven't printed any support filaments yet. Yeah, but yeah, this next one's going to have nearly 100 new materials of all kinds of wacky and wild stuff. And most of this you can't even get here in the U.S. At least not without importing it. There's crazy stuff. We got PPSU. We tried to print this on stream, or we thought we were printing peak, but it was actually PPSU, and that raised all kinds of hell. This one is labeled as nylon 230. Nylon that can be printed at 230 degrees. It's Tolman's naming is very creative, and by that I mean no.
Creative.
Yeah, Gabger11 was says, so you were saying the every filament title was clickbait. I'll admit it, I'm a professional YouTuber. Oh man, it's I wasn't. I'm not going to say it was baloney, right? Because I'm not going to say it was baloney. It was more like every filament that is reasonable to expect people to print. This is a lot of this is the unreasonable stuff. There's a reason why you never heard of a lot of this, because a lot of it's a total nightmare, and a lot of it's not. Some of it's not even. Yeah, here we go. Some of it's not even 3D printer filament. This one was printed in Weed Whacker, like hedge trimmer line, which.
Well, that's where Tolman Nylon came from in the first place, right?
Really?
Yeah. Yeah, you should go read his original Rep forum posts.
Huh. I didn't know he came out of the Rep. Yeah, Tolman's Nylon's products and their their polyester products are great. Yeah, the Weed Whacker filament. This actually printed really well, like really well. It's except for it has some. There was a bit of a layer split. Here we go. Yeah, there's a bit of curling and a layer split near the back. But apart from that, this is one of the best looking prints of all. Yeah. Just like it's just weird. But yeah, there's so many friggin' filaments here. So did you manage to find the paper?
Yes, I posted it in the chat. So essentially, and hear me out here, because this is going to sound ridiculous when I say it. And when this guy said it to me at first, I was like, bullshit, dude, I don't believe you. But I've been soundly proven wrong. And I'm going to give him a shout out. Andy Gleedle from University of, I don't want to get it wrong. Is that Loughborough, not Sheffield? I always say Sheffield, but it's actually Loughborough. Luga Baruga for you Australians or Americans. He basically came to me and was like, I think that I've proven that layer adhesion in the Z direction has nothing to do with temperature, polymer bonding, like welding and all of that. It's all down to just one thing, which is the amount of plastic that's touching itself in Z, just cross-sectional area in Z. And I was like, no, like, you know, the temperature and the energy and the welding and the, like, you've got to have enough heat to like make the bond and all. No, turns out total horseshit. And we've all been talking out our asses for years, and Andy has cracked the code. So the reason why plastics seem to have greater Z direction strength when we print them hotter is they just drop in viscosity, which means that it flows more into the layer below. It's got nothing to do with the additional heat helping with additional bonding. And so Andy has sat there and painstakingly like SEM fracture surface after SEM fracture surface. And I was like, dude, no one's going to believe you. Even if you are right, no one's going to be like, I didn't believe you. And like,
I mean, it makes sense.
And say this, you're going to have like one hell of a body of evidence, because this is a big deal.
Right.
And so he sat there and fracture surface, experiment after experimentation, and built these amazing, and this is what this full control G-code designer thing is about. He programmed his own G-code, like almost like a superset of a slicer that creates these single wall test coupons.
Right.
And did those at different, like the papers are amazing. And
so this guy systematically printed the same material hundreds of times, different speeds, different temperatures.
Every single way, like layer width, height, like pressures, speeds, temperatures. And what it really comes down to is like one of the last figures in the article, which is just SEM fracture surface area versus Z direction strength.
Sanjay, if you like to share the paper, I can put it in Stream Chat if you throw it in.
Now, interlayer bonding has bulk strength.
Yeah, you have to send it to me. Can't send it to you can only I personally can post directly to YouTube.
Oh God. There's
a chat button in the bottom tray.
I'm not good at the internet. I'm trying, Zach. I'm trying. Here we are.
There we go. Oh, yeah, there we go. Awesome. All right, I'm just going to copy that, and I'm going to put that into chat right here. And
I can just hear, like, the people in the comments are going to be there, like, no, it can't be true.
Oh, you almost got beaten by someone with an archive link. There we go. Sorry for making your face go back and forth. There's no way to tell Zoom to only pay attention to you. It has to capture the window, or tell OBS. Yeah, that's interesting stuff. And it kind of makes sense. Like intuitively, it makes sense because you got materials like TPE that are not the materials like TPE that you'd think would, like, they have a lot of flex and stuff. They kind of pull themselves apart, but the layer adhesion from TPE and TPU is bananas. It's the best,
Yeah.
and it makes sense that the thing that they have in common is just straight up viscosity.
Yeah.
Yeah,
It's such an
acrylic,
elegant,
right? Like
it's such an elegant theory.
PMMA has terrible
Yeah.
layer adhesion, even though it's a pretty rigid material. Because yeah, I would imagine, yeah, it's just super low viscosity out of the nozzle. That's really interesting.
Yep. And he also went all the way down to the simulation of the fundamental energy state of the polymer and the welding, and essentially, as long as you make the plastic be next to each other at anything close to printing temperature or above its like liquidus state, like it gone bond, and it really doesn't make much of a hoots difference. Like
Huh.
yeah.
Oh, I gotta try. That's interesting. What the flux from the comments says. So if only the amount of filament contacting in Z matters, are you saying the speed you print at doesn't affect the print strength in any way? And from the sound of it, it's the opposite.
But no, like this is the thing. So if anything that you are doing is preventing you from squeezing what the plastic that you're laying into intimate full contact. That's right, you heard me. Intimate full contact with the layer below. You've got to like massage it in there, boys and girls.
You want as the highest percentage layer contact as possible.
Correct. The critical factor is the amount of plastic you have touching plastic, skin on skin.
So now that I'm thinking about it, like does this mean that like we've kind of been screwing? So like when you're using, let's say, a 0.4 millimeter nozzle, right? Your line length is approximately 0.4 millimeters. So does this mean we've kind of been screwing ourselves, like because we should be over extruding a bit?
Yeah, there's a really solid argument to be made for that. So for a given layer height, your interstices, i.e., this is going to really suck to explain a three-dimensional geometric construct in words. So I'm going to give it a go. You have, if you look at a track in cross-section, you have a shape called a stadia, the shape of a stadium, a rectangle with rounded end caps.
Right.
So
I'm going to pull
this. If this is like the XY direction and that's Z, you have this stadia. And then if you stack your stadia next to each other, and you put a bunch of stadia on top of each other as well to form, say, a perimeter of a normal cube, i.e. the plural of them is stadium. Yes, exactly that. If you stack a bunch of those on top of each other and next to each other, you're going to end up with the gaps, i.e. the interstices.
Probably this bit and this bit. I just want to point out, like, I just like to read Wolfram's definition of this because it's great. A stadium, also called a disco rectangle, oblong, or sausage body, yada yada yada. So can we call these sausage bodies? Is that
disco rectangle?
Disco rectangle.
Pixels in the background. We can have a rectangle disco. But okay, so you got your disco rectangles. For a given layer height, your interstice, i.e. the gap. So if you stacked a bunch of those stadiums next to each other, you would have a four-pointed kind of star-shaped gap in the middle.
This is showing
right?
me as Google's stupid game console.
But did you kind of get, you'd have that like four-pointed star?
Yeah.
So for a given layer height, you get the same sized interstice. And this is a half truth, because if you actually go and section the things in XY, it's a lot more complex than that. But because it's not a pure stadia interstice, it's a different shape. But the point remains is that for a given layer height, every single interstice is the same amount of surface area in Z that you're giving up. And so if you, for a given layer height, print at a wider extrusion width, therefore producing fewer interstices, you increase the amount of area that is just exists in Z.
This bit right here.
Have I explained myself adequately shittily enough for you?
So yeah, basically, so what you're saying is that like the taller the, let's see, so the taller the layers are, the more of a void there is at the edge of the edge of the extrusion line.
Argumentum ad absurdum, take it to its other logical extreme. If you print with an extrusion width that is so small such that you don't have a disco, rectangle, or brown stadia, you just have a circular cross section and lots of circles stacked on top of each other, your contact surface area in Z is 0.
Right, this bit
and
right
that's
here.
what you try and do with supports and rafts. You try, but you fail. So that is the logical extreme in bringing the extrusion width in to as small as you can, and creating these line contacts.
Right.
And then if you go completely the other way, and you just have,
so
only a single extrusion width, then you will have 100% surface area contact. Impossible, but.
So Ian Ross from the comments is asking, could a square nozzle help, or will surface tension just pull it round? I imagine no.
So yeah, it's you can't. The dirty little secret of the hot end land is that the shape of the nozzle isn't always super impactful. In this kind of situation, it's not super impactful. In others, it is, but. In a lot of most regimes of flow and deposition, the predominant factors are the flat tip on the nozzle, and its planarity, its smoothness, and its ability to lay down and squish the layer. And then you have at the edges the viscosity of the polymer itself forms that round cap.
So it's interesting. So how does the rubber hit the road then? Gabriel 11 asks, so would larger nozzles provide better layer adhesion? Everything else held constant.
I
guess
larger nozzle.
I guess it depends more on the width of the line of plastic leaving the nozzle. Than the nozzle itself.
Yes.
So that's really interesting. I guess this also helps explain why there's a sweet spot for layer height as well.
Yeah, if you want to maximize strength, you kind of want to have the largest extrusion width you can get away with for your design or Z direction strength. And this is where we get into the complexities of.
So I guess this raises another thing that I guess this kind of had its day in the sun. Haven't seen anyone talk about it in a while, but for a while it was all anyone was asking me about, and that is remelting, dumping burying your part in salt and baking it, annealing, all that stuff.
Yeah.
Do you think this is worth it, or you think it's better to just use a stronger plastic?
Is it worth it? Is, I guess, a very application-specific criteria. Does it increase isotropy in terms of the strength of the part? Yes, dramatically. Because the part will pull more of itself into contact, because of the energy state of the polymer, it will want to pull itself into the lowest surface area state that it can.
Right.
And so it will try and pull itself into a single homologous spherical blob. And then you constrain it in salt or plaster or whatever it may be.
Keep it from fully collapsing in on itself.
Yeah, and it will flow into itself and produce near isotropic parts.
Yeah, so
is that worth it? I don't know.
Yeah, because I don't know, like I feel like, if I'm using PLA, if I'm using PETG and it's not strong enough, like I'm not gonna spend 2 hours burying it in salt and shoving it in the oven. I'm just gonna print it in polycarbonate or something.
Performance per unit hassle, right?
Right. Yeah, that's true.
Like this is the great, like this is why I think that FDM is the big underrepresented, underestimated, ugly duckling of the additive manufacturing.
You think it's just because we haven't found the right? You think it's because we haven't found the right materials? Because I think a lot of folks think
I think that we're very
they'll never
close,
scale
right?
up because the machines are too slow.
But the great joy, speed isn't the important thing. It's your productivity per unit dollar invested in the machinery to set up, and it's your productivity per incremental dollar spent in order to produce the parts, i.e. capex, setup cost, and ongoing incremental cost. FDM is the winner by an order of magnitude versus every other additive manufacturing process on both counts.
Probably for certain quantities, because I imagine, like, if you use I don't know, if I commission, like, an aluminum injection mold, and that thing can make 15,000 parts, that, like,
oh yeah, I was saying versus other additive manufacturing
right, versus trying to 3D print 15,000 parts. Like, I feel like the first one would probably take a week or two, and the other would take, depending on, like, I don't know, I guess if you had 500 printers, like, it would still take, depending on the size of the printer, it would still take
how much is an injection molding line? Not just the tool, but an actual injection molding line itself, a whole line.
That's gonna be expensive.
About 250 to 500,000, let's say. Let's call it 300,000. And imagine that you buy, $1,000 $300 Prusa Mini
right.
and 3 Pro-E type machines. Now you need to produce your 15,000 parts. So you spent 300 grand, and you either have one injection molding machine with one tool, or you have 1,000 Prusa Minis, and each of those 1,000 Prusa Minis need to print 15 parts in a row. The glorious part here is that with your Prusa Mini approach, you don't have to have gotten $300,000. You maybe only started with $1,000, and you bought 3 machines, and then you found a market, and you scaled it to 5 machines, and slowly, you
can bootstrap a manufacturing operation.
Right, and the neat part is the amount of capital expenditure that you require scales the quanta of manufacturing. And this is just like expanding with AWS or Google App Engine or whatever. Like, you can buy a small, low-cost, incremental amount more manufacturing process capability to cope with demand on demand. And then you can rapidly deploy, undeploy, and change and modify in a very agile way.
Yeah, I hope this
is that you're making.
I guess I hope this is something that ends up being relevant, because intuitively I'm thinking that the world can only move in one direction, and that is consolidation, fewer companies making larger numbers of products, less customization, more standardization, because the economics of scale are just so overwhelming, and companies are just becoming so powerful that the fact that we have such a diverse assortment of products
and PCB manufacturing, right? Look at I think FDM is gonna do for plastic parts like what the PCB ways of this world have done for integrated circuits. not what I see, like as in PCBA. That like ability, yes, there's an amount of centralization, but also they're delivering like mass customization in effect.
I hope that I hope the economy supports that. Like, I hope there are enough people who want and will pay for custom stuff to make that happen. Because, like, look, we're makers here. We love the idea of adding some creativity to your consumerism.
Things sound like boutique and impractical, but certainly we are seeing more and more of FDM being used in a manufacturing practical end use case parts production situations by more and more of our big customers. Like, we see the writing on the wall with what they're asking us, what they're developing and putting in their machines, what their future machines look like,
right?
And are supporting. And we're talking about big names supporting big trends, and it's not like one or two are going in one direction and a few are going in the other. Every big, credible, respectable name that we serve, which is most of them, I would say. Certainly every major Western 3D printer brand that I know of is looking at FDM as a more scaled manufacturer of end-use parts system.
Oh, that's pretty interesting. I guess there's another element of this that if you have,
I have no doubt. I have literally zero doubt. Like, to me, this is like the least, like most. There's not even a debate in my head as to where this ends up. Like,
it's true. I mean, you're seeing the other side of it.
Yeah, and like we have the immense privilege of working with some amazing companies and seeing. We have a unique insight, but to my mind, this is such a foregone conclusion that I'm not even going to sit here and debate it with you. Like,
fair enough. I guess like one of the dynamics that one of the dynamics at play here, I think, is how import and export friendly the countries are, because I know it's just so like I feel it. Correct me if I'm wrong here, but I think one of the challenges of mass production 3D printing is the fact that it takes manpower to actually run all those. Like one person can supervise one person in a country with, let's say, light regulations can supervise like 3 injection molding machines that can churn out thousands of things per hour. But I'd imagine it takes an entire team to keep a couple thousand 3D printers running. So, do you think that whether or not you think that like how this develops depends on the cost of labor available? Because there's no way something like that could be very profitable here in the United States, where like you'd have to pay everyone $15 an hour. But then again, like I'm thinking that like if you were to run this overseas. Like, even still, like, I imagine it's a lot cheaper to set... Like, I imagine here in the States, it's cheaper to set up a 3D printing, like a print farm, than an injection molding line. So, I don't know. I think the whole thing's kind of interesting. Yeah, it's a weird dynamic, because, I don't know. Like, I studied this stuff when I was in... I studied this stuff when I was in school, and the fixed cost, like... At the time, like, the fixed cost favored injection molding to such an extent that, like, professors were like, just make your company make plastics, because, But I can imagine the math changing, especially as if the country becomes a little less import friendly.
I'm gonna. Well, imagine that you didn't need all of those people. That's all I'm gonna say.
Fair enough. Yeah, 3D printers are definitely very high maintenance now. The math would change a lot if they were more set it and forget it.
Wouldn't it just?
Yeah, I feel like that's
The
another.
maths would change a lot.
Yeah, in the
Imagine
hobby, in
if
the
you
hobby
didn't
sphere
need
too.
if you didn't need a team of people.
Yeah, right.
Yeah,
Like
the
modern
maths
3D
would change a
printers
lot.
are really high maintenance. Even something like dealing with a clogged nozzle can tie someone up for like 20 minutes. But
Right.
yeah, and I think
And
for hobbyists too, like there are and I feel like most people who watch my show are pretty much locked out of the hobby because of how much time it takes. Like they're just like very few, not everyone's so lucky that they have the money to be able to afford the stuff and the time to do it. And stuff like 3D printing, like sure, it would be accessible if you could just start a print before you go to work and play with it after you come home. But I mean, what are the odds that your printer will succeed with completely unattended? Really, like 80%, right?
yeah, but I think also if you're um, producing multiple of a single part instance, or if you are doing many variants of a single base design,
Right.
then you can do quite well at qualifying and pre-understanding that part. And so and this is the same with injection molding. There's an immense amount of tweaking and fiddling with the molds and the like shot temperature and size and pack and hold pressures and like all sorts of stuff. To tweak it until it just runs and it ejects every time and the part sticks on the core, comes out the cavity, and the ejectors run and all your gates. Like that takes a while to tweak in. And it may be that that's the case when you're initially setting up a job.
Right.
But once you make it sing, then I see very little reason why there aren't huge opportunities for reduction or elimination of labor.
That's really interesting. So
So I'm dancing around a bunch of
fair enough.
things
I want to bring up
here. But to talk about like what we're looking at as E3D, like we're really, really heavily investing in making sure that E3D extrusion systems are the system that you would want on a scaled manufacturing platform.
Huh? You think that's the future? Because I know like most of the hype of 3D printing has been, oh, everyone's gonna get their own 3D printer, and we're never gonna need a whole manufacturing industry again, which is complete baloney. So you think that
Yeah.
but you think that the future is 3D printers in factories, not 3D printers in hacker spaces.
Factories is again a dangerous word, like, but there's this like little twilight zone between the hacker space and what you and I like, what the word factory conjures up in your head, which is what FDM is doing and small run PCB manufacturing is doing, and like putting small pick and place machines and so it goes and so it goes,
Right.
and low cost CNC milling, and all of this is leading to a situation where an idea or a product can be brought to life with fewer people in less space with less money. And so application specific ideas or problems that are common to a lower total number of people can be solved by products as the solutions. So problems that exist among a fewer number of people, it now will make sense to solve those problems for those people with products, because you will be able to bring about or bring into life a hardware product that solves whatever that problem
The
may be.
return of the hardware startup.
Yes.
Can only
But
as
instead of the hardware
as an
socket, I
ex-prototype
think,
developer, I can only hope.
but I think that, as like as Elon says, like making a prototype is easy, but manufacturing something at scale is very, very hard. And what we're doing is gradually beating and bending and breaking FDM from being a one-off prototyping production system to something that you can develop, prototype, iterate, and produce on in a single common process.
Could be
And that to me is
interesting
very,
future.
very exciting.
What are some applications? Do you see any like new applications of 3D printing that just seem preposterous now? Like I feel like I'm constantly talking about how right now 3D printing a circuit board is a ludicrous idea. But
Yeah,
could
yeah,
that be
I would agree
could that
with
be
you.
the future?
Um, I don't know. Like, I think that going all the way back to how I started this episode with, like, as Alexander Slocum would say out of MIT, that the material science has to exist first, and we have to have the
It's true.
material science.
Can't put
And
the
so,
cart before the horse.
yeah, until there is some great material science breakthrough that allows us to somehow process useful electrical conductors and all of the other things that go into
It's true.
circuit manufacturing. Until we get there, I think that that's probably a pipe dream.
It's gonna
But
stay science fiction for now. Yeah, the material science does have to kind of lead the technical. Like the machine can only be as good as the stuff you run through it.
yeah.
So, but
Well,
so
actually, no.
we're coming to the end of
This is
our time. We'll keep this going, but like for everyone who is listening and watching, now is an excellent time to post your questions in the stream chat, so that we can relay it along. But yeah, so we're talking about materials that could facilitate circuit printing.
well. So one of the things of the materials that are only good as the machine that they're made. One of the really cool things that, or fundamental concepts that is common to the mark forged and desktop metal and like all those sintering metal filaments, and also to carbon, their thermal SLA system, is they are separating the material science part from the geometric forming part. And this is really critical. And I would love to see more of this in FDM beyond just metals. So in the print and sinter systems, you have a machine that cannot print metal, but it prints a surrogate geometric body that then goes into a second machine and second process that converts that surrogate geometric body into a high performing material.
Oh, that's really interesting.
So in the FDM system, so what you're doing is decoupling the geometric forming process from the high performance material science process, rather than doing them in the same machine. So in the case of the print and sinter processes, you print this precursor material that then goes on to become sintered into pure metal. But you don't have to process high temperature metals inside your print head. And then in the carbon
that's
SLA,
true.
thermal SLA process, you effectively have, and this is a gross oversimplification, but you have something that's like epoxy mixed in with SLA resin, and you print it like it's an SLA resin, and you are basically capturing tons and tons of epoxy inside your SLA part, to the point where it's only a fraction SLA resin and maybe 80% epoxy.
Huh.
And then afterwards you take it and you put it in the oven, and all the epoxy reacts. And so the SLA bit is doing the geometric forming process, and then the oven does the high performance epoxy thermosetting plastic bit. And those are the only two examples that I know of. One, and actually there's another one involving circuit boards, funnily enough, which is the system where they've got tons of advertising. They print the ink, it turns into the
Oh,
circuit.
it's oh man,
Volterra.
their name is really hard to remember. It's really generic. I know the exact
Volterra.
one. Yeah, it looks like a 3D printer, but it's got a syringe with the silver
Yeah,
conductive stuff in it. Someone's gonna
yeah,
name it.
Volterra.
Someone's gonna put
Um,
it. Someone's gonna put it in the comments. I just know it.
and
Uh,
um,
Volterra. That's right.
yeah,
Yep.
um,
Drew Shark and Sam Saddleoff. Yeah, it's
and
Volterra.
Voxelate. Yeah, Voxelate also do much the same thing.
What do you think? So, and Voxelay, yeah, Practical Printing pointed that one out. So, what did
So
I guess like so.
this, I think, is going to be. I'm going to have to go in a second
All right.
because I've blown. I'm meant to be on holiday, and my couple of friends are out here on the barbecue.
Oh no! Oh yeah, the sun is setting. The
I
barbecue is.
promise.
All
Sorry,
right.
I've just been nerding out with Zack about plastic.
Well, let's I suppose we should let you go. I really appreciate your time. This has been really fascinating.
Yeah.
We got to keep an eye out for those mass manufacturing lines of 3D printers, and more importantly, those composites with the spherical and flexible additives. Those seem like the ones that are going to change everything.
To look forward to. And then I think that final frontier is coming up with amazing material science innovations that like separate the geometric forming process from the material science thing, so we can free ourselves of the limitations of what we can do inside of a printhead or on a, inside of a SLA resin when a photon hits it. And
exciting stuff. So where should people go to keep up? So where should people go to keep up with all this? Should they follow you on social media? Do you have anything to pimp or promote?
Gosh, I don't even know where you go to keep up with all of this. I think that if you're really into this in terms of doing it at scale in industry, I think that AMUG is the place to be, Additive Manufacturing Users Group. So if you're interested in this in a professional context, AMUG is definitely the place to be. And coming to trade shows and talking to people in those kind of contexts.
So what about E3D? Where should folks go to keep up with what the company's up to? Because
yeah, in terms of what we're getting up to, definitely our Twitter, our Discord, and watch a space on the YouTube front. There's a bunch of really neat stuff coming up on YouTube. We have, as I've been alluding to a lot, a ton of pent-up products that have been developed over the kind of COVID period that are on the way.
Oh boy.
And all of them heavily oriented towards what we firmly believe, I would say almost going beyond the word believe towards like think that we know is the future of FDM's place as a manufacturing technology.
And you guys are E3D online like everywhere.
Correct. Yep, exactly. E3D online.
Oh man, yeah. There's got to be
out for our sick new.
Don't tell me you're going to make a tool changer with five extruders. I'd murder you.
No, we're not. But we're going to make something that brings a lot of that power to the everyman without all of the hassle. A subset, not the full set. You've got one, Zack. Don't sit there looking like you're.
Hey, I'm just trying to maintain OPSEC over here.
Yeah.
I'm not saying nothing. You guys are gonna have to show up on wait around my mailbox, the rubber hose. Anyways, thank you. That's fascinating stuff. Yes, I've been sent some pretty spicy stuff. You guys, gals and cyborgs will hear about that once I've cleared it with the mothership. But yeah, there's some cool stuff. Yeah, E3D also sent me a bunch of spicy filaments that are going to show up in the next every filament video. So yeah, thanks a lot for joining in on the show.
I'm gonna go be sociable with my friends.
All right. Well then, let's. Any final words for our viewers?
Oh no, you can't play that. I'm still online.
Sounds like the words are being given for you. All right, I'll let you go. Thanks a lot for being part of the show.
I'm definitely gonna go. I'm gonna get someone into trouble, and it probably will be me.
All right, I'm gonna stay broadcasting.
Yes, once
for a
I'm
bit.
off the stream.
Take it easy.
Bye.
I hope the food is still edible. And then there was one. So yeah, thank you so much to Sanjay for generously contributing some of his time. E3D is working on a whole lot of super spicy stuff, and really excited to get a chance to share some of that in the future. At least for now. Yeah. I feel like I'd be kind of shortchanging everyone by cutting the stream out right here, even though I have a ton of work to do for the next video. So I'm thinking like let's poll the audience. Should we tie it up here, or should we maybe keep things going for a little bit and maybe try to run a print or two? One of the things that I think that was really funny. Yeah, Sanjay knows like everything there is to know about like material stuff. I thought that his observation about the additives was really cool, because part of doing this every filament episode. Oh, hang on one sec. I'm just gonna grab this guy. Yeah, part of doing this every filament episode and forcing myself to really get every with the filament is trying all kinds of stuff I never even heard of before, such as materials of flexible additives and materials of spherical additives, and they really do print better. It wasn't some baloney. One of the things we didn't talk about that I found really interesting was materials that combine support and combine dissolving and conventional materials. This right here is called Grolay, and it's a combination of PVA, PLA, and wood sawdust. And it basically, when you throw this thing in water, when you throw this guy in water, it dissolves the PVA, and you can grow plants on it. So this is a chia pet. This is a chia pet. And there's all kinds of these crazy filaments. The state of technology is crazy. Anyways, so Dewey asks, will you do more interviews about additive manufacturing? Yeah, I plan on making guests a regular part of this show, because especially as we move forward and we start to do projects that are basically less photogenic, we should say. I plan on bringing on a lot more guests in and out of 3D printing. Like this isn't a strictly 3D printing channel, but because in the future I've got an upcoming project that. Well, it's gonna be one of the most elaborate projects we've ever done on the channel. It's gonna be sick, but it's almost all programming, and we've got a bunch of really interesting interviews and chats planned to keep up with that. So a lot of interesting stuff going on here. Real quick, Veldorg asks, synthetic spider silk filament when? I've been trying so hard to get a hold of some spider silk filament, and I've spoken to some researchers who published a paper on it. It's just not practical to make in a large enough quantity that they could practically send it over. It involves like some really complicated, some sort of like bacterial genetic engineering stuff. Christopher Garcia says, if you can't buy spider silk filament, guess you have to make your own. I've been capturing every spider I can find, but I just don't think I can get enough of them to make a 1.75 millimeter filament before they start dying. I have a lot harder time capturing flies than spiders. Yeah, this is a lot of fun. I think this is a lot of fun. Really good guest. I think Mad Dog says, "Keep it going. Do a behind the scenes to the next episode, stream and print a benchy." You know what? I think we should. I think it actually makes sense to bring this one to a close fairly soon, because in part, I think it would just be kind of awkward to keep everyone waiting here, and yeah, keep everyone waiting here while I set up 2 materials in this printer. And also, I'm so far behind schedule in the next episode, it's freaking me out. So yeah, I'd like to thank everyone for dropping in on today's stream. I know it's a bit of a shorter one, but you know, I think I don't think everything has to be an all day thing. That said, I'd like to add something new to this particular stream, and that is thanking our patrons, because well, I mean, they're super supportive. We've been making all the videos public, right? We've been making we've been making all the videos, all the stream replays public. The patrons voted on it, and I just my schedule is just too crammed to make extra content. So I think it's only fair to thank them for their contribution. So yeah, thanks a lot to all of our patrons. You've been seeing them scroll back there. If you'd like to join them, visit patreon.com/Zack Freedman. Our lab assistant supporters are, in no particular order, Katz, Daniel Cadwell, Victor Vaughn, Connor Barnes, Acalia, PowerShell is better than Command. Oh, them's fighting words. Nito Gansitano, Protagonist, Mark Whittington, Robert Breeze, my Yiddish mama, my dog is a bear, Varka, Kevin DeGraff, Philip, Period Clots, Rusty Flute, Autismo, BLM and Friends, Joe Harp, The Antifa, Sir Derpington of Derptopia, Zoster, C. Harris, Good Suck. Reagan says, "Don't say my name backwards, it's a bad word." Alright, I won't. Jason Llewellyn, SXP, Guygasm, Brad Cox, the world's greatest drone pilot, Bot Grinder FPV, Taranac, Chrome Runner, Powerful CCH, Michael Roche, SA6 Ham, I gotta figure that, Sex Ham, Michael Dunn, Nathan Johnson, One Handful of Beans, Olivia Yipdong, Frantic Fanatic, Talin, Democratic Socialist, and a Pretty Righteous Dude, Azundo, Bob Dobbington, E. Punman, Zach, Lydia K. Trans Rights, Roger Pinkham, Eddie Zanforian, and, last but not least, Bill Schooler. And we cannot forget our profoundly generous collaborators, Jeremy Arnold, Schweddy Veg, Chuck Fadouk, Small Dong, I'm Not Bedicor, Command, and introducing Brian D. Swollen Nut. I have been instructed that the 3 very, very generous collaborators who have practically unspeakable names are friends and are pooling to support me, and I really appreciate this support. The channel is these filaments did not come cheap, and this stuff would not happen without super duper generous patrons. Chris Tuttle, thank you so much for your super chat. Your previous video, you had PEI with glue stick to capped on tape. Did it work? No. No, I ended up having, so yeah, we had you might be thinking of a couple different things. There was one where we were struggling to get something to stick to a plate. It turned out that the plate itself had become too contaminated, and after a thorough scrubbing with soap and water, it worked fine. Second, we now have nanopolymer adhesive, which I bought to help ultra-high temperature material stick to the bed. But it turns out to get pretty much anything to stick to pretty much anything. It's basically super glue. So that has... I know that stuff is pretty much like slammed the door on any peeling and print problems, and I found out that Joel, the 3D printing nerd, has also started using it obsessively too. A bunch of folks are suggesting that I get in touch with the Thought Emporium. I am far too small potatoes to reach out to a YouTuber of that caliber, but I appreciate everyone's faith in me. Reagan, thanks a lot for buying something off my Amazon wish list. Got me some diagonal cutters that have really come in handy to clean up some of these boats, because my old ones are super duper well, they're crap. So yeah, I really appreciate that. Rebecca Hogue asks, whatever happened to the print you did in resin? Maybe I missed the update. Let me, you know what? Let's while I've got some folks' attention, let me see if I can find the thing. I think I threw it in here. Yeah. So it turned out that this is a benchy printed in PET, made of recycled soda bottles, and this is a benchy printed on the Rheology Halot Sky, and you can see that this thing came out absolutely perfectly. This is definitely the nicest benchy of any of the ones that that I've printed so far. And yeah, it's gorgeous. It said no support. Focus now, please. Yeah, this has no supports. There is no, I mean, no supports, no nothing. I just literally put this thing on the bed. There you go. It was great. Yeah, it was. Yeah, it's pretty sick. We are going to be doing a lot more resin printing. Although I have a bunch of FDM prints. Oh, we had a question about my schedule, and you were completely right about it. Wait, where is it? Where is it? Where is it? Where is it? B Fingit asks, when's the next video? 2 weeks out. Next video is supposed to be tomorrow, but Brooke had, I'm not going to blame. Basically, it was supposed to be 2 weeks out, and I've been having a tremendous amount of trouble printing all these filaments. And we got and we fostered another dog who has been freaking out and barking his face off and keeping me up all night. And Brooks, some of Brooks' family came to visit, and I mean, it just goes on and on. We've just had so much interference it's made it impossible. My goal is to try to get that video, to the sponsor for approval on Monday and have that out sometime next week. So, yeah. Fortunately, it's the name of the game. Printing all these filaments is just, I mean, making a video like this is just a huge amount of time. It kind of comes with the territory. I am trying to accelerate the pace at which we do videos, but it's just not happening. Oh, Brooke wants to show off the pups. Brooke wants to show off the dog. Let me try to get our dog cam in position. Dog cam, go. Let's see. Oh, we still have the... Hang on one sec. I'm just going to switch over here so we can make this... that's not what I wanted at all. I've got to make this smaller. There we go. Boop. All right. There we go. This is Edmund. This is Edmund is afraid of this room. There are a lot of strange smells and sounds, and oh, you're such a good boy, Edmund. Oh, he's licking me. I'm being licked. Yeah, this is Edmund. He's Peter's brother, and he's also available for adoption. So yeah, if you're in the Colorado area and you'd like to adopt a very, very sweet pup who really likes licking everything, visit the Good Dog Rescue. Yeah. His brother's behind him. His brother has a stupid cone on his head because he just got fixed. Yeah. Those are so yeah, they are the Voidstar Labradors. I think we're not totally sure what kind of dogs they are, but there's a little lab in there, at least a bit. Yeah, but oh, they're the sweetest. He's wearing the cone of shame, and at least he's smarter than Roscoe, like a previous foster Roscoe. He got his cone, he just ran full throttle into everything. But oh yeah, these guys are super adorable, and we're keeping Peter. We decide he's just too sweet. But Edmund is up for adoption. So if anyone would like a very sweet dog, then reach out to the Good Dog Rescue. Yeah. But anyways, thanks to everyone for tuning in. I think this was a lot of fun. Sanjay was a real blast to talk to. And yeah, I'll see you folks on Monday, and then soon after with the next video. What do we have coming up on Monday? I only have it. So next Monday I have it written here as boats. I just have it printing more and more boats. Oh yeah, I still have another client project too. Basically, there's tons of stuff going on right now. I'm totally overloaded with crap. I'm going to be busting my butt over the weekend to try to bring you content as rapidly as possible. And yeah, you'll see that, and hopefully me, in the future. You folks have an excellent weekend. I hope you finish all of your projects, and I'm going to be here running off boat after boat. Yeah. Take care. Have fun. And I'm out of sign-offs. Yeah, get out of here. Get lost. Go drink a beer or something. Go get some sun. Take a swim. Adopt a dog. Steal a dog. Just steal your neighbor's dog and take it out for a walk. He's not going to mind. Bye-bye.